Welcome back to the deep dive.
Incredible. It's a true library of the cosmos.
It really is. It covers everything from, mysteries right here in our own cosmic backyard to the absolute edge of the universe and the beginning of time itself.
And that's our mission today, isn't it? To take this huge stack of information, astrophysics, geology, biology, and sort of synthesize it.
Exactly. We're going to cut through the noise, connect the dots, and deliver the most essential, mind-expanding nuggets of knowledge. This is the ultimate shortcut.
I love that. So we'll start close to home. We'll tackle some of those persistent myths and explore some really surprising discoveries about the planets.
And then we zoom out.
Then we zoom out. We'll get into the search for alien life. And, looking for everything from their atmospheric smells to their giant engineering projects.
Wow, okay.
And finally, we'll confront the really big cosmological questions, the ones that our newest telescopes like the JWST are forcing us to ask.
Okay, I'm ready. Let's do it. So, where do we start this journey?
Let's start with what feels most familiar, but is maybe one of the most misunderstood.
Right.
Our own moon.
And the Apollo missions, after all these decades, you still hear the conspiracy theories. It seems like a good place to set the record straight.
Absolutely. And the two biggest arguments you always hear are about the photos and the radiation.
Let's start with the photos then. The classic argument is, if they were really on the moon, where are all the stars?
It's the first thing skeptics point to. And on the surface, it feels like a legitimate question. You look up at the night sky from Earth, you see stars. The moon has no atmosphere, so the sky should be filled with them, right?
It seems totally counterintuitive that the sky in the photos is just pitch black.
It does. But the explanation has nothing to do with being on a soundstage in Nevada and everything to do with Photography 101.
So it's a technical issue, not a celestial one.
Precisely. You have to remember what the environment is like. The lunar surface, when the sun is out, is brilliantly, blindingly bright.
I've heard it compared to a sunny day on a white sand beach or fresh snow.
That's a perfect analogy. You've got direct, unfiltered sunlight hitting this light gray dust. So to take a picture of anything in the foreground, the astronaut in his white suit, the shiny lander, you have to use camera settings for a very bright environment.
Which means what, exactly? A really, really fast shutter speed.
Incredibly fast. We're talking shutter speeds of 11,000th or even 12,000th of a second.
Okay, wow.
The whole point is to let in just a tiny bit of light so that the foreground isn't completely overexposed, just a giant white blur.
And the stars, as bright as they might seem to our eyes in the dark, are just incredibly faint points of light in comparison.
Infinitely fainter. So at that super fast shutter speed, their light simply doesn't have enough time to hit the film and make an impression. It's like trying to photograph a firefly next to a searchlight.
You're only going to see the searchlight. The firefly is just, it's not going to show up.
It's not going to show up.
Yeah.
The camera was set up to capture the important scientific data on the ground, not the background scenery.
And I think what really seals this argument for me is that we actually have counter evidence, right? There are pictures from the moon that show stars.
We do, and it's from an unlikely source. The Soviet Lunokhod rovers.
The unmanned rovers.
Exactly. These rovers had telecameras with an automatic exposure system. So when the rover's camera happened to point up at the empty black sky, what did the camera's light meters see?
It saw nothing. Absolute darkness.
Total darkness. So the automatic system did what it was designed to do. It thought, I need more light, and it opened the shutter for a much, much longer time.
And when it did that,
the stars appeared. Perfectly clear. It's the ultimate proof that it was always just about the camera settings, not about the location.
That really should put that one to rest for good. Okay, so let's move on to the second big claim, which feels a lot more serious. The radiation. The Van Allen belts.
Yes, the argument here is that the astronauts would have received a lethal dose of radiation crossing these belts that protect the Earth.
And these belts are no joke. They're real, and they are dangerous.
Oh, absolutely. They're these massive donut-shaped regions of highly energetic charged particles trapped by Earth's magnetic field. There are two main ones.
An inner and an outer belt.
Right, and the inner one is the real problem. It's full of high-energy protons. These are heavy, fast-moving particles that can do serious biological damage. The outer belt is mostly lower-energy electrons, which are easier to shield against.
So how on Earth did the Apollo crews get through the most dangerous part, the inner proton belt, without getting sick or worse?
It came down to two things: speed and trajectory. It was all about exceptionally careful mission planning.
They didn't just punch straight through the middle of it.
Not at all. The belts are most intense near the Earth's magnetic poles and weaker near the equator. So the Apollo missions were launched on a path that stayed relatively close to the equator.
So they were already aiming for the thinnest, weakest part of the belt.
Precisely. And then there's the speed. When they did the translunar injection burn, that's the big rocket firing that sends them out of Earth orbit towards the moon, they were moving incredibly fast.
They basically just zipped through the worst parts as quickly as possible.
They crossed the most dangerous inner belt in a matter of minutes. You spend a bit more time in the outer, less harmful electron belt, but the whole passage through the worst of it was over in just a few hours.
And the spacecraft itself provided shielding.
Of course. The command module was robustly shielded. When you add it all up, the carefully chosen path, the high speed, the shielding, the total radiation dose they received over the entire week-long mission was minimal.
How minimal are we talking? Is it comparable to anything we'd understand?
It's comparable to the annual safety limit for a worker in a nuclear power plant. In some cases, it was even less. It was a known hazard that was meticulously engineered around.
And the proof is in the pudding. The Apollo 8 crew did it first in 1968, flew around the moon, and came back perfectly healthy.
They proved the flight plan worked. The radiation argument, just like the photography one, falls apart as soon as you look at the actual physics and the engineering.
Okay, let's leave the moon behind and push deeper into the solar system. I was fascinated by the material on the ice giants, Uranus and Neptune. Even their name, ice giants, is apparently up for debate now.
It is, which shows you how science is always refining itself. The name originally came from the idea that they were made up mostly of what astronomers call ices.
Which isn't just frozen water, right?
Right. In astronomy, ice refers to volatile compounds like water, but also methane and ammonia. The theory was that these planets were mostly a giant slushy core of these materials under immense pressure.
So they're not giant ice cubes, it's more about their chemical makeup.
Exactly. But the latest models, the new calculations of their internal density and structure, are telling a slightly different story.
What's changing?
It looks like they might be significantly more rocky or stony than we first thought. The models suggest they have a much larger, denser, rocky core than was predicted, meaning rock makes up a bigger percentage of their total mass.
So ice giant might be a bit of a misnomer. Maybe they're more like rock giants with a thick icy mantle.
That's a much more accurate, if less catchy name. It really forces us to rethink how they formed and what the distribution of materials was in the early outer solar system.
And it's not just the planets themselves that are surprising us. Their moons are proving to be some of the most active and interesting places out there. Everyone knows Europa and Enceladus, but one of Uranus's moons, Ariel, is a real dark horse.
Ariel is fascinating, especially because we know so little about it. Our best look came from the Voyager 2 flyby back in 1986.
A single fleeting glance decades ago.
A single glance. And from those few photos, scientists have pieced together a compelling case. Ariel is tiny, about 3 times smaller than our moon, but its surface shows signs of massive geological activity.
Kind of signs.
We see huge fault lines, ridges, and canyons, some of them miles deep, crisscrossing the surface. For a small, icy world that should have frozen solid billions of years ago, that kind of tectonic activity means there has to be a source of internal heat.
And internal heat on an icy moon points to one thing.
A subsurface ocean. The model suggests that tidal forces from Uranus could be keeping the interior warm enough to sustain a vast liquid water ocean, maybe over 150 kilometers deep, hidden beneath that fractured icy crust.
That's incredible. An ocean world hiding out at Uranus based on a few photos from the 80s.
It puts Ariel squarely on the map as a prime target for future missions looking for life.
Speaking of active water worlds, let's go back to Enceladus. Cassini gave us those spectacular images of the water geysers erupting from its south pole. But the sources say we learned something profound about how those geysers work. They're not just constant, are they?
No, they're regulated. They have a pulse. Cassini's long-term observations show that the intensity of the plumes changes in a predictable cycle.
And that cycle is tied to Saturn.
It's all about tidal forces. Enceladus is on an elliptical orbit, so sometimes it's a little closer to Saturn, sometimes a little farther away.
And Saturn's immense gravity squeezes and stretches the moon.
Like a cosmic stress ball. When Enceladus gets to its closest point, the gravitational pull is strongest, and it literally pulls open the cracks, the tiger stripes, at the South Pole.
And the geysers erupt with more force.
Exactly. More water vapor and ice particles blast out into space. Then, as Enceladus moves farther away, the tidal stress lessens, the cracks squeeze partially shut, and the flow of the geysers diminishes.
So Saturn is acting like a planetary heart, pumping the plumbing system of its own moon.
That is a perfect way to describe it. It's this beautiful, dynamic, tidally driven system that's actively feeding one of Saturn's rings with icy particles. It's one of the most active hydrological systems in the solar system.
Let's move inward now to Mars. The story of Mars is always the story of the search for water, and for a long time the best evidence for current water seemed to be those dark streaks on crater slopes.
The recurring slope lineae, or RSLs. Yes, for years they were the smoking gun. They would appear in the Martian spring, flow downhill, and then fade in the winter. They looked for all the world like seasonal flows of wet sand.
The idea was that it was some kind of super salty brine that could stay liquid in the cold.
That was the leading hypothesis. Salt dramatically lowers the freezing point of water. But there was a bigger physical problem, one that the physicists kept pointing out: atmospheric pressure.
Right, the Martian atmosphere is incredibly thin.
It's barely there. The pressure on the surface is about 1160th of what we have here on Earth. And at that low pressure, liquid water is it's not stable.
What do you mean by not stable?
I mean, even if you could magically get the temperature above freezing, the low pressure means liquid water would instantly violently boil. The part that didn't boil away would flash freeze due to the rapid evaporative cooling.
So it boils and freezes at the same time without ever really existing as a flowing liquid.
Exactly. It can't persist.
Yeah.
So whatever is causing those streaks, it's highly unlikely to be flowing water. The consensus has shifted now to them being flows of dry sand or dust cascading down the slopes.
So the hope for surface water today is fading, but the search for signs of ancient life in places that once held water is more exciting than ever.
Absolutely. And that's all about the Perseverance rover in Jezero Crater.
Which we know was a big lake billions of years ago.
An ancient lake fed by a river delta. The perfect place to look for fossils. And Perseverance has drilled into the mudstone, the fossilized sediment from the lake bed, and found something very, very intriguing.
These are the leopard spots, right?
That's the nickname scientists have given them. In the rock core samples, they see these small, dark circular features with lighter colored centers.
And why is that pattern significant?
Because on Earth, when you look at ancient mudstone, very similar patterns are often biosignatures. They're linked to microbial mats or other structures formed by colonies of microorganisms interacting with the sediment.
So it's not a fossil of a creature, but a fossil of the effect a creature had on its environment.
Precisely. Now, we have to be cautious. It could still be some weird abiotic mineral formation we haven't seen before. But it's the most compelling morphological evidence, the most promising shape for ancient Martian life we have ever found.
And those core samples are now sealed and waiting for a ride home.
They are cached on the surface, waiting for a future mission to pick them up and bring them back to Earth. Once we get those in the lab, we might finally get an answer.
Let's do one more stop in the inner solar system at the oddball planet, Mercury. It's just a strange world from a compositional standpoint.
Mercury is a total anomaly. It's incredibly dense for its size. And the reason is that it has this absolutely colossal iron core.
It's mostly just a giant ball of iron with a thin, rocky crust.
Essentially, yes. The core takes up something like half the entire planet's volume. For comparison, Earth's core is large, but proportionally much smaller. The puzzle is, if the planet is so iron-rich, you'd expect its surface to be too. But it's not. The surface has very little iron.
So how do you get a planet with a giant iron heart and an iron-poor skin?
The leading theory is that Mercury used to be much bigger. It started out as a more normal planet with a standard ratio of rock and metal. But then, very early in its history, it suffered a catastrophe.
A giant impact.
Either a giant glancing blow from another protoplanet that stripped away most of its outer rocky mantle, or it formed so close to the young, hyperactive sun that the intense heat and solar wind literally boiled its rocky layers away. Either way, what we see today is the exposed, naked core of a much larger original planet.
That history also connects it to one of my favorite stories in science. The hunt for the phantom planet, Vulcan.
Ah, yes, the planet that wasn't there. It's such a great lesson in the scientific method.
It started with a real problem, right?
Yeah.
Mercury's orbit wasn't behaving as it should.
It wasn't. Its orbit precesses, meaning the closest point of its orbit to the sun, shifts over time. And astronomers calculated that it was shifting just a tiny, tiny bit faster than Newton's laws of gravity predicted, even when you accounted for the pull of all the other known planets.
And this is where the famous astronomer Urbain Le Verrier comes in.
The same man who had, just years before, famously predicted the existence and location of Neptune just by looking at similar weird wobbles in the orbit of Uranus. He was a rock star.
So he figured if it worked once,
It'll work again. He hypothesized there must be another undiscovered planet orbiting even closer to the sun than Mercury, And its gravity was giving Mercury that extra little tug. He named it Vulcan.
And people searched for it for decades.
They did. They'd looked for a tiny black spot transiting across the sun, but they never found it. And the reason is, there was no planet. The problem wasn't with the map of the solar system. The problem was with Newton's map of gravity itself.
Enter Albert Einstein.
In 1915, Einstein's general theory of relativity showed that massive objects like the sun don't just pull on things with gravity, they literally warp the fabric of space-time around them. And when he calculated how Mercury would move through that warped space-time,
The numbers matched perfectly.
the missing precession was explained entirely by the curvature of space around the sun. It was the first major observational proof of general relativity, and it closed the book on Vulcan forever.
Let's shift our focus now from the planets themselves to the other stuff flying around. The near-Earth objects and the interstellar visitors.
Our ability to track these things is getting scarily good. We're moving from just discovering them to actually predicting where they'll land.
You mean we can forecast a meteorite fall?
We can. Over the last decade or so, astronomers have successfully predicted about 10 of them. And the lead time is getting shorter and shorter.
What's the record?
Not long ago, a meteoroid about 1 meter across, big enough to make a nice fireball, was spotted just 3 hours before it hit the atmosphere. 3 hours. That's an incredible feat of observation and rapid calculation.
And that kind of capability is essential for planetary defense. Which brings us to the DART mission, the first real test of deflecting an asteroid.
An incredible success story. The mission was to slam a spacecraft into Dimorphos, the small moonlet of the asteroid Didymos, and see how much we could change its orbit.
And the results were surprising, weren't they? It worked better than expected.
Much better. The initial models were based on a simple kinetic impact. The momentum of the spacecraft hitting the asteroids, like a game of cosmic pool.
But something else happened that amplified the effect.
A whole lot else happened. It turns out Dimorphos isn't a solid chunk of rock. It's what we call a rubble pile, a loose collection of boulders and dust held together by gravity.
So it's not a cannonball, it's a beanbag.
A perfect analogy. So when DART hit, it didn't just create a crater. It plunged deep inside and triggered this massive explosion of material, a huge plume of ejecta that blasted out into space.
So it's the recoil, the ejecta flying one way, pushed the asteroid the other way.
It acted like a powerful rocket thruster. That reactive force from the plume of debris gave the asteroid a much bigger push than the initial impact alone. It's game changer because it means we might be able to deflect even larger asteroids with relatively small impactors as long as they have this porous structure.
That's a huge lesson. Now, there's a much more subtle force at play on these rocks, something called the Yarkovsky effect.
This is one of my favorite bits of science history. The effect was first figured out not by an astronomer, but by a Polish-Russian civil engineer named Ivan Yarkovsky in, 1900.
What was an engineer doing thinking about asteroids?
He was a polymath. And he applied his knowledge of thermodynamics. He realized that sunlight itself could act as a tiny engine to push asteroids around.
How does that work?
It's quite simple, really. Sunlight heats the afternoon side of a rotating asteroid. As that hot spot rotates into the night side, it radiates that heat away as infrared radiation, as thermal photons.
And photons, even though they have no mass, have momentum.
They do. So that stream of infrared radiation leaving the surface gives the asteroid a minuscule but constant push in the opposite direction.
And over millions of years, that tiny push adds up.
It adds up to a huge change. It can slowly alter an asteroid's orbit, pushing it either closer to or farther from the sun. It can even speed up its rotation. We've seen some small meteoroids spinning incredibly fast, completing a rotation every few seconds, and we think the Yarkovsky effect is what spun them up over eons.
It's amazing that a force so small can have such a profound impact on the architecture of the solar system.
It's the tyranny of long timescales.
Okay, let's talk about the real outsiders, the interstellar visitors. Oumuamua back in 2017 was the first, and it's still just so strange.
Oumuamua is still a head-scratcher. The central mystery was its acceleration. As it flew away from the sun, it was speeding up, but not in a way that gravity alone could explain.
It had some kind of non-gravitational push. With a normal comet, that would be the gas jets from sublimating ice.
Exactly, you'd see a coma, a tail. But Oumuamua had nothing. It was just this inert object that was mysteriously accelerating.
And that's what opened the door for their really exotic explanations.
It did. The most famous, of course, came from Avi Loeb at Harvard, who suggested it could be an artificial object, A piece of alien technology, maybe a thin solar sail being pushed by the pressure of sunlight itself, which would explain the acceleration without any gas.
But there are natural explanations too, right? They're just
Most, the
weird.
most plausible natural explanation is that Oumuamua was made of something we don't typically see in our comets, like solid nitrogen, a chunk of nitrogen ice like you'd find on Pluto.
And nitrogen gas would be invisible to our telescope.
Completely invisible, so it could have been outgassing and accelerating, and we just wouldn't have been able to see the jets. It's a clever solution, but it implies it came from a very, very different kind of planetary system.
Now, in 2024, we got our second confirmed visitor, 3I Atlas. And this time, we had better tools ready to look at it.
We had the full Arsenal JWST, Hubble, the VLT in Chile, and 3I Atlas was clearly a comet. It had a tail, it was active. But when we looked at his chemistry, it screamed, not from around here.
What was so unusual about its composition?
It had a staggering amount of carbon dioxide. Compared to comets from our own solar system, it had something like 16 times more CO2 than water.
Wow, so that's like a chemical fingerprint telling us about the stellar nursery it came from?
It's a direct sample of the building blocks of another planetary system, where CO2 ice was clearly far more abundant than water ice was here. It's an incredible piece of data.
And there was also something strange about its trajectory, wasn't there? Something that got the alien proponents excited again.
There was. At one point in its journey through our inner solar system, its orbit took it behind the Sun and then behind Venus, from our point of view.
So it was hidden from our telescopes for a period?
Exactly. Now, this could absolutely be a coincidence of celestial mechanics, but the more speculative interpretation is that this trajectory was designed to allow it to observe our system while being hidden from view.
A sort of stealthy flyby?
It's a long shot, but it's an intriguing possibility that keeps the mystery alive.
This is a perfect bridge to our next topic, astrobiology. The search for life is getting so much more sophisticated.
We're moving beyond just looking for water. We're hunting for specific chemical clues, biosignatures. And one of the most exciting targets right now is an exoplanet called K218b.
This is a mini Neptune in the habitable zone of its star.
Right. It's bigger than Earth, likely has a deep hydrogen atmosphere, but it might have a liquid water ocean on its surface. And the JWST took a look at its atmosphere and found a hint of something remarkable.
Dimethyl sulfide, DMS.
Yes. And on Earth, DMS is overwhelmingly produced by life, specifically marine phytoplankton. It's literally the smell of the sea.
So finding that in the atmosphere of an alien world would be monumental.
It would be the strongest evidence for extraterrestrial life we've ever found. The implication would be a massive, planet-wide ocean teeming with something like our algae.
But there's always a but in science, isn't there? There's some controversy here.
There is. We need to be very cautious. First, the detection was based on a very faint signal in the data. It was right on the edge of statistical significance, so we need more observations to confirm it's even real.
And second, even if it is real, does it have to be life?
That's the critical question. We now know that DMS can be formed through non-biological or abiotic processes. We've detected it in comets and even in cold interstellar gas clouds. So before we can claim life, we have to prove that there isn't some unknown exotic geochemistry in K218b's high-pressure atmosphere that could be producing it without biology.
The bar for proof is and should be incredibly high.
Extraordinarily high.
Let's bring the search closer to home, to Jupiter's moon Europa. We're almost certain there's a huge ocean there, but the radiation environment is just brutal.
It's a nightmare for astrobiology. Jupiter's magnetosphere pummels Europa with a constant fire hose of radiation that would destroy any complex organic molecules, like amino acids or DNA, on the surface in a very short time.
So even if ocean water wells up and freezes onto the surface, bringing signs of life with it, that evidence gets erased almost immediately.
It gets sterilized and destroyed. So how do you look for it? You can't just land and scoop up some ice.
The sources mention a very clever solution. Look for the toughest molecules around.
Exactly. You look for the organic molecules that are most resistant to radiation. And it turns out that a certain class, the aromatic amino acids, are particularly tough.
What makes them so tough?
They have a ring-like structure in their chemistry, a benzene ring, that makes them much more stable and resistant to being broken apart by radiation. Experiments show they could survive for hundreds of years, just a few millimeters under the surface ice.
And the idea is to use lasers to find them.
Yes, a future lander could use a powerful laser to vaporize a tiny bit of the surface ice and then analyze the plume. These aromatic amino acids would glow or fluoresce in a very specific way when hit by the laser, allowing us to detect them even in tiny concentrations. It's a brilliant way to work around a very hostile environment.
Speaking of hostile environments and potential biosignatures, let's talk about Venus and the phosphine puzzle.
This was a discovery that just came out of left field and shocked everyone. Radio astronomers detected phosphine gas, pH3, in the clouds of Venus.
And on Earth, phosphine is very strongly linked to life in oxygen-free environments.
It is. We don't know of any significant geological process that makes it, so finding it on Venus was a huge red flag for potential biology. And it was found at a very interesting altitude, about 50 to 55 kilometers up.
Why is that altitude so important?
Because up there, the conditions are surprisingly Earth-like. The temperature is around 0 Celsius. The atmospheric pressure is about the same as at sea level on Earth. If life were to exist on Venus, that's where it would have to be.
But the giant killer question is, how does it stay up there?
That's the paradox. The surface of Venus is a hellscape, over 460 degrees Celsius. Any microbe in the clouds is going to be denser than the surrounding air, so it's naturally going to sink.
And if it sinks too low, it gets cooked.
Instantly destroyed. So for a microbial ecosystem to survive, it would need some kind of active biological mechanism to keep itself aloft, to fight gravity and stay in that temperate cloud layer. And we have no idea what that could be. That's why the phosphine signal remains a deep and fascinating mystery.
You know, all this talk about habitable worlds often centers on planets like ours, around stars like ours. But our sun is actually a minority player in the galaxy, isn't it?
It really is. Our sun is a G-type star, a yellow dwarf. And these stars are fantastic for life. They're stable, they burn for billions of years, giving complex life plenty of time to evolve. But they only make up about 10% of the stars in the Milky Way.
So what's the other 90%?
The vast majority are red dwarf stars, M-types. They're much smaller, cooler, and dimmer than the sun. And while they are incredibly numerous and live for trillions of years, they are terrible neighbors for life.
Why is that? What makes them so bad?
They are violent, especially when they're young. They erupt with frequent, powerful stellar flares that are much more intense relative to their size than our suns.
And any planet in the habitable zone of a cool red dwarf would have to be orbiting very, very close to it.
Right in the line of fire. A planet close enough to have liquid water would get periodically blasted with sterilizing radiation and have its atmosphere stripped away over time. So while simple life might cling on, it's a very tough environment for complex, high-level life to get a foothold and thrive over geological time.
It really puts into perspective how fortunate our own stellar situation is.
It's a key piece of the Fermi paradox puzzle. Maybe the stable environments needed for intelligence are much rarer than we think.
Let's take that final leap now out to the deepest reaches of space and time. Let's talk cosmology and the Big Bang.
The Big Bang Theory is the foundation of modern cosmology, and it's incredibly successful. It's important to start there. It made major predictions that were later confirmed.
Like what? What are the cornerstones of its proof?
Two huge ones. First, it correctly predicted the abundance of the light elements in the early universe, that it should be about 75% hydrogen and 25% helium. And our observations matched that perfectly.
And the second one is the afterglow of the Big Bang itself.
The cosmic microwave background, the CMB, the theory predicted this faint, uniform radiation should be left over from when the universe was just 380,000 years old, and in the 1960s, we found it. It's a perfect match. The core idea is rock solid.
Our newest telescope, JWST, is seeing things that are causing some tension with the theory.
Tension is the perfect word. The issue isn't with the Big Bang itself, but with the timeline of what happened after. JWST is looking back to the cosmic dawn and seeing galaxies that appear to have formed just 200 to 300 million years after the Big Bang.
And that's too early.
According to our current models of structure formation, yes, it's way too early. The models of how primordial gas clouds should collapse under gravity to form the first stars and galaxies predict the process should take much longer. These galaxies are too big, too bright, too well formed, too soon.
So does this break cosmology? Do we need a new theory?
No, and this is the key point that often gets lost in popular media. It doesn't mean the Big Bang is wrong. It means our understanding of how structure forms, how the first galaxies lit up, is incomplete. We need to refine the model. Maybe dark matter played a different role, or the first stars formed more efficiently.
We're tweaking the details, not throwing out the whole framework.
Exactly. And to really confirm the ages of these ancient galaxies, we need better data. We need what are called spectra.
And that requires an even bigger telescope.
It requires a monster. The Extremely Large Telescope, or EELT, being built in Chile. Its main mirror will be 40 meters across, the size of a basketball court. It will have the light-gathering power to capture the faint spectra from these first galaxies and confirm their exact distance and age, which will allow us to finally fix our models.
Speaking of things we can't see, let's talk about dark matter. It's the biggest elephant in the cosmic room.
It's 85% of the matter in the universe, and we still have no idea what it is. We certainly ruled out a lot of things.
The early hope was that it was just normal stuff that's hard to see, right?
Right. The idea of Macho's massive compact halo objects. This was the theory that our galactic halo was just filled with dim things like black holes, dead white dwarfs, or faint brown dwarfs. Normal matter, just not shining.
And we looked for them.
We did, using gravitational lensing surveys. And we found some, but nowhere near enough. Not even close to the amount needed to explain why our galaxy rotates the way it does. The conclusion was inescapable. Dark matter has to be something else entirely. Some new, exotic, undiscovered particle that doesn't interact with light at all.
Let's shift from a missing particle to an excess one. We detect more positrons, the antimatter version of electrons, in cosmic rays than we expect. Where are they coming from?
That's a great puzzle with the likely answer. The excess positrons are almost certainly being generated by nearby pulsars.
Pulsars are spinning neutron stars.
Rapidly spinning, hypermagnetized neutron stars. They are incredible particle accelerators. But the key clue is that they have to be nearby pulsars.
Why nearby? Why can't they be coming from across the galaxy?
Because positrons lose energy very quickly. As they travel through space, they interact with the faint starlight and background photons that fill the galaxy, and this interaction saps their energy. So if these positrons were coming from thousands of light years away, they'd arrive here with very low energy.
But we detect them with high energy.
Very high energy, which means they couldn't have traveled very far. They have to originate within a few hundred parsecs of us. And that points the finger directly at a handful of powerful, active pulsars in our local galactic neighborhood.
Neutron stars are just laboratories for the most extreme physics, and they're linked to another huge mystery: fast radio bursts, or FRBs.
FRBs are they're mind-boggling. They are millisecond-long bursts of radio waves from distant galaxies that can, in that tiny fraction of a second, outshine our entire galaxy in the radio spectrum.
A colossal amount of energy released in the blink of an eye. What could possibly do that?
The leading candidate is a special kind of neutron star called a magnetar.
As the name implies, it's all about the magnetic field.
These are the most magnetic objects in the known universe. Their magnetic fields are quadrillions of times stronger than Earth's. The theory is that the immense stress from this magnetic field can cause the star's crust to suddenly crack a starquake, which unleashes a titanic blast of magnetic energy that we see as a fast radio burst.
And we're seeing other forms of stellar violence that are challenging physics. There was a gamma-ray burst in 2022 that sent particles to us that shouldn't have been able to make the journey.
That's right, a gamma-ray burst from about 2 billion light years away. And detectors here on Earth registered photons from that event with energies up to 250 tera-electron volts, or TeV.
That's an insane amount of energy for a single particle.
It's comparable to the energy of collisions at the Large Hadron Collider. And the problem is, a photon with that much energy traveling for 2 billion years should have interacted with the faint background light of the universe and lost most of its energy.
But it didn't. It arrived here almost fully charged.
Which suggests one of two things. Either the universe is much more transparent to high-energy gamma rays than we thought, or there is some new physics, some unknown particle property that allows them to survive that incredible journey intact.
From unpredictable explosions, let's turn to one we might actually be able to predict: a nearby supernova.
Yes. Stars like Betelgeuse or ticking time bombs are going to explode, and it's just a matter of when. And it turns out we'll get a warning.
How can we get a warning for something that happens in the core of a star, hidden from view?
Because of neutrinos. In the final days before the core collapses, the fusion reactions go into overdrive, producing an unimaginable flood of neutrinos.
And neutrinos barely interact with anything. They'll fly right out of the star's core at nearly the speed of light.
Instantly. While the light and the shockwave are still trapped deep inside. So our giant neutrino detectors, the one under the ice in Antarctica, the one in Lake Baikal, they will suddenly see this massive burst of neutrinos from the direction of that star.
And that's our alarm bell.
That's the 2-day warning. It tells astronomers, point every telescope you have at this star right now. And it tells mission control, get your astronauts on the ISS to a shielded part of the station, because a wave of hard radiation will follow the light. It's a cosmic early warning system.
Let's turn now to maybe the biggest question of all. Are we alone? The Search for Extraterrestrial Intelligence, SETI.
And the search is getting much more creative. We're not just listening for a hello message anymore. We're looking for technosignatures, evidence of massive industrial-scale alien technology.
And the ultimate technosignature has to be the Dyson sphere.
The classic. Yeah. The idea that a truly advanced civilization would eventually need all the energy from its parent star, so it would build a megastructure, a shell, or a swarm of collectors to capture 100% of it.
If a civilization did that, their star would just disappear from view in visible light, wouldn't it?
It would. But thermodynamics tells us that energy can't be destroyed. All that captured stellar energy would heat up the structure itself.
So the sphere would glow.
It would glow brightly in the infrared. So the search for a Dyson sphere is a search for an object that is dark in visible light, but is an incredibly bright, powerful source of waste heat.
This whole idea got a huge boost a few years ago with Tabby's star.
It did. KIC 8462852.
Yeah.
A star that was showing these bizarre, deep, and irregular dips in its brightness. Sometimes it would dim by over 20%.
And the most exciting, if unlikely, explanation was
an incomplete Dyson sphere under construction. A massive swarm of artificial objects was orbiting the star, blocking its light in strange, non-periodic ways.
What's the more sober scientific explanation now?
The leading theory is a natural one. It's likely that there was a massive collision of planets or planetesimals in that system, creating a gigantic, uneven cloud of dust and debris that is orbiting the star and causing those weird dips. Less exciting, but probably more likely.
Beyond looking for megastructures, the sources also suggest we should listen for their noise, unintentional signals.
Exactly. Don't just look for a deliberate message. Look for the byproducts of their technology. Think about our own planet. We leak signals into space all the time.
Powerful radar systems, for example, military or air traffic control radar.
Those are perfect examples. Powerful pulsed signals that aren't meant as communication to the stars, but are strong enough to travel interstellar distances. If an alien civilization has similar technology, say an anti-missile defense grid, we might be able to pick up the hum of their planetary operations.
But if we were to try and communicate actively, the distances are just a killer.
The distances are brutal. To send a signal that's strong enough to be heard across light years of cosmic noise, you have to transmit at an incredibly slow data rate. We're talking speeds like an old dial-up modem. A few bits per second.
So a real-time conversation is completely off the table. It would take decades or centuries for a round trip.
Forget about it. Which leads to a different idea for sharing information. The data capsule.
Instead of talking, you mail them a hard drive.
That's basically it. If conversation is impractical, maybe the best approach is to create a durable, information-rich archive. You could encode all of human knowledge, our science, our art, our history, onto small, robust probes.
And then just scatter them through the galaxy.
Like seeds, a galactic message in a bottle. The hope is that millions of years from now, someone might find one and learn that we existed, even if we're long gone. It's about preserving knowledge on a cosmic timescale.
And if we do send a message, what language do we use? What's the universal tongue?
It has to be math and physics. It's the only thing we can be sure another technological species would understand.
That's why things like the Arecibo message were built around prime numbers.
Prime numbers are a concept of pure logic. They're not a human cultural invention. An advanced civilization will have discovered them. You can also base a message on fundamental physical constants, like the wavelength of hydrogen, which is the most common element in the universe. It's our only real shot at a common language.
Let's bring it back to the present day and our own technology. Russia is updating its rocket fleet with the new Angara A5.
They are. It's their new heavy-lift rocket designed to replace the old, reliable, but highly toxic Proton rocket. It's a big step forward, but its performance is a little bit hampered by geography.
How so?
It launches from the new Vostochny Cosmodrome, which is in the Russian Far East. It's at a much higher northern latitude than the Baikonur launch site they used in Kazakhstan.
And launching closer to the equator is better.
It gives you a free boost from the Earth's rotation. Launching from a high latitude means you have to use a lot more fuel to make the big plane change maneuver to get satellites into that valuable geosynchronous orbit over the equator. So it comes with a performance penalty.
Looking at rocket tech more broadly, it seems like the future is all about methane.
Methane is the fuel of choice for the next generation. SpaceX's Starship uses it, and many others are following. And there are two huge reasons why.
What's the first one?
Reusability. Methane burns much, much cleaner than the traditional kerosene-based rocket fuel. Kerosene leaves behind a lot of soot and gunk that clogs up the engine plumbing and requires a lot of refurbishment.
And clean-burning methane means you can turn the rocket around and fly it again much faster and cheaper.
Exactly. But the second reason is the real game changer for going to Mars.
In situ resource utilization, making your fuel on-site.
You've got it. The Martian atmosphere is mostly carbon dioxide. There's also lots of water ice in the soil. Using a chemical process called the Sabatier reaction, you can combine the carbon from the atmosphere with hydrogen from the water ice to create methane fuel.
So you don't have to haul all your return trip fuel with you from Earth. You make it when you get there.
Which fundamentally changes the logistics and economics of a Mars colony. It's the key to becoming self-sufficient off-world.
Finally, let's talk about new telescopes and new ways of using old data. There's a new space telescope called SPHEREX.
SPHEREX is really cool. It's not a super high-resolution telescope like Hubble or Webb. It's a surveyor. Think of it as a coarse filter for the universe.
So it's about quantity over quality.
Exactly. It's designed to map the entire sky multiple times over its 2-year mission, taking a low-resolution spectrum of every object it sees. The goal is to build a massive 3D map of the cosmos.
How many objects are we talking about?
The plan is to get spectra for 500 million galaxies and millions of stars. It will create an unprecedented catalog of where things are in the universe and how far away they are.
So it finds the most interesting targets for the big telescopes to go look at in more detail.
It provides the context. It finds the needles in the cosmic haystack for JWST to go and study.
And it's not just new instruments. We're finding incredible value in just reanalyzing old data with modern tools.
This is one of the unsung revolutions in science. We can take data from decades or even centuries ago and, using modern software and AI, pull out so much more information.
What are some good examples?
The old lunar orbiter photos from the 1960s, they were taken on film, developed in orbit, and then scanned and beamed back to Earth with pretty primitive tech. But we still have the original film. By rescanning that film with modern high-resolution scanners and applying advanced image processing, we've created images of the moon that are vastly superior to what they had in the Apollo era.
And this even works with handwritten logs from the 19th century.
It does. AI has been trained to read the unique, often difficult handwriting of 19th century astronomers from their observation logs. By digitizing those records, we've extended our detailed knowledge of the sun's activity cycles back by decades, giving us a much better long-term baseline. It's like scientific time travel.
We have covered such an incredible range today, from the details of a camera shutter on the moon to the fate of the entire cosmos.
It really shows how relentless the search for knowledge is. And if we want to look at the longest possible timescale, there's one prediction we can make with almost absolute certainty.
The ultimate fate of our sun.
And by extension, the Earth. The physics of stellar evolution is very well understood. Our sun is getting slowly but steadily hotter, about 7 or 8% more powerful every billion years.
And in about 3.5 to 4 billion years, that process kicks into high gear.
The sun runs out of hydrogen fuel in its core, and it will swell up into a red giant. It will become hundreds of times its current size.
Now, I've heard there is some debate about whether Earth would be consumed. The idea that as the sun expands, it loses mass, so its gravity gets weaker, and Earth's orbit moves outward.
That's true, it does. The Earth will drift outward slightly. But the latest, most precise calculations show it won't be enough to save us. The sun will still expand far enough to first engulf Mercury, then Venus, and then it will reach and consume the Earth.
The end of our planetary home is a scientific certainty, a sobering thought.
It is, and it leads to one final, provocative idea to leave you with.
Let's hear it.
When we use a telescope like JWST, we are looking billions of years into the past. We can literally watch the universe evolve from those first faint galaxies to the structures we see today. We can understand the past, and as we just did, we can predict the very distant future.
We can see the whole timeline, in a way.
Almost. But what's the one thing we can't see? The one boundary we can't cross.
The moment of the Big Bang itself.
Or even before it. The ultimate puzzle that current physics has no answer for is what happened in that moment before the beginning. What was the state of things that led to the Big Bang? That remains the final absolute frontier.
And that, learner, is your deep dive for today. Go forth and ponder the greatest questions of the cosmos.